Okay, folks, let's get started. How's everybody doing today? Good. Anybody doing bad? Nobody wants to say they're doing bad? Badly? Okay, so how can we improve it for you? No class today?
Sorry, Kevin, what did you ask?
I asked how I could improve it for those who are doing badly.
A joke? You have a funny joke?
A joke?
A joke.
If you guys are really, really good, I might tell you a joke later, okay? But you have to be really, really good. Okay, we'll see. Actually, I have a cute joke. I'll tell you later, so I'll do that. Okay. All right. So we are talking about enzymes. And enzymes, I hope I left you the impression the other day, are pretty remarkable things. And we're going to get some glimpses about how they do the magic that they do by understanding something about structure function, and also later talking about mechanisms of catalysis. Okay? Now, we have an exam a week from today, and I haven't decided exactly how far we're going to get through this for the exam, but it will likely be through the lecture on Wednesday. That's my tentative plan. I will let you know on Wednesday. It kind of depends on how far I get today. Okay. So enzymes are catalysts. Catalysts change reaction. And you might wonder, what's the difference between an enzyme and a catalyst? Well, they both catalyze reactions. And enzymes are catalysts in the sense that they catalyze reactions. They speed them up without themselves being changed. So is there any difference at all? There is. And one of the things that you're going to see is that enzymes transiently get changed. Okay? During the mechanism of catalysis, they are transiently changed. And that is something that doesn't happen to a chemical catalyst. Now, that's a little further ahead from where we are right now, but that's what's coming as we get talking about that. Okay. Well, when we talk about enzymes, we have to think a little bit about energy. And I know you guys had delta G and all that stuff in freshman chemistry to some extent, thermodynamics. We're not going to go into that right now. So you're not going to do any delta G calculations for this exam. Okay? We're only going to be talking about delta G in very simple terms, and the second exam we'll have some delta G problems. Okay? And I think you'll discover that the delta G problems are actually not that difficult, especially once you've gotten Henderson-Hasselbalch under your belt. You will definitely have Henderson-Hasselbalch problems on your exam. Well, delta G, of course, is the change in Gibbs free energy. And the value of the delta G tells us tremendous things. It tells us directions of reactions. And since biological reactions can go forwards or backwards, biological reaction going forwards in one case might mean it's breaking something down. In the backwards direction, it might be making something up, building something. So that direction becomes very important for a cell to be able to control a metabolic pathway. If the delta G for a reaction is less than 0, I'm sure you know the reaction proceeds forward as written. If the delta G for a reaction is greater than 0, the reaction proceeds backwards as written. And if the delta G for a reaction is equal to 0, the reaction is at equilibrium. Notice that last point there. Equilibrium does not mean equal concentrations of reactants and products. How that message doesn't make it through freshman chemistry, I don't know. Chemistry ought to be beat on the head for that. Okay? Even after I've said that, a good third of you are going to try to tell me on the exam that equilibrium means equal concentrations of products and reactants. It's not. Equilibrium means that you reach a steady state where there's no change in concentration of reactants and products. You might have 10 times as much reactant as product, or 10 times as much product as reactant, but at equilibrium, that ratio stays the same. It doesn't change anymore. Okay? So remember that. Delta G, equilibrium does not mean equal concentrations of products and reactants. Okay, delta G 0 prime. All right? Delta G is different from delta G 0 prime in that delta G 0 prime is the standard Gibbs free energy. All right? Well, what's delta G? Delta G is the delta G is the change in Gibbs free energy. Delta G 0 prime is the change in the standard Gibbs free energy. Okay? The standard Gibbs free energy is the same as delta G under standard conditions. They're exactly the same under standard conditions. Okay? So these two are linked in an equation that says delta G is equal to delta G 0 prime plus RT times the natural log of products divided by reactants. Basically, that's what it says. Okay? If products equals reactants, then delta G 0 prime equals delta G because the natural log of 1 is equal to 0. Okay? So delta G is the same as delta G 0 prime under standard conditions. And those standard conditions include when products equal reactants. Notice I didn't say equilibrium. I said the two are the same when products equal reactants. All right. Now we're going to come back to that. I'm not going to go through that further here, but I do want you to know that there's a difference between delta G and delta G 0 prime. Delta G is the delta G under any conditions. We change the temperature. We change the concentration of products and reactants. We now have delta G, okay, that we can determine for a reaction. Delta G is only delta G at standard. So delta G 0 prime is a constant for a given reaction. Just like pKa was a constant for a given weak acid dissociation, delta G 0 prime is a constant for a given reaction. It's always the same. Okay, well, let's talk now about how this relates to mechanism. I have to introduce that because the mechanism I have for describing to you about enzymatic rates involves a consideration of energy. Okay? Here's a kind of a dumb figure. It shows how the amount of product in a reaction is increased with enzyme. Well, if you have a catalyst, obviously you know that's going to happen, right? You see that after a while it levels off. And the reason it levels off we'll talk about, but it does sort of level off with time. How does an enzyme work? Well, this figure I think is one of the best figures around to describe to you how an enzyme works. So I'm going to sort of step you through it, and then I'm going to give you an example about how that you can visualize this. This figure shows us plotting on the y-axis free energy. So it's a sort of a measure of delta G. It's sort of a transient delta G that they call delta G double cross here. With reaction progress, meaning that the longer this goes, we can think of this as time if you want to on the x-axis. When the reaction starts, I've got A goes to B. Okay? When the reaction starts, I have A, and down here I have B. So the substrate is the material that the enzyme binds to and catalyzes a reaction on. A starts here. It gets down to B over here. Now, there's an old cartoon that used to be out there that was a scientific cartoon. And it was this long, big mess of equations on the board. Okay? And then over here was the answer to the problem. And in between was this thing that says, and then a miracle happens. Okay? So I don't want you to think that there's a miracle happening here. There are some things that are happening that we'll talk about that are specific. Okay? But for the moment, I want you to think, well, there's a transition that's occurring in going from A down to B. So there's a transition. And that transition is called a transition state. And we associate with that a transition energy. We can think of this as there's a certain amount of energy that this intermediate molecule must acquire before it falls down the slope and goes down over here. You see two different transition energies. The first transition energy is the uncatalyzed reaction shown here. And the second one is for the catalyzed reaction. What this tells us is that this enzymatic catalyst is lowering the transition state energy, or the transition energy. You can use those terms interchangeably. So there's no change. There's no change. There's a reduction in the amount of energy necessary to get to the transition state using an enzyme. Well, in the real world, how does this matter? Well, in the real world, it's a little hard to visualize, but I have an example I'd like to give to students. Imagine, if you will, that I have, sitting here in this room, a giant ball bearing. Okay? It's about 12 feet wide. It's stainless steel. Okay? Now, in theory, I should be able to take this ball bearing outside, and if there weren't trees in the way, push it towards the Oregon coast, and it would roll there because we are a couple hundred feet above the sea level, and it would get there. Well, you see some problems, right? It's not a straight shot down to the Oregon coast. If it were, then yes, it would simply roll all the way down there. So you say, well, we've got to get this ball bearing, so that it can make it to the coast. So what we should do is we should take the ball bearing, and we get all the people in this class, and we go and we push it to the tallest peak, so that we know when it gets there, assuming there's not trees in the way, it's going to eventually get down, 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 and roll all the way down to the coast. And we could do that. So if we went to Mary's Peak, which is the tallest nearby peak, we could push this ball bearing to the top of Mary's Peak. We have a path cut through it. And even though it might hit some other hills along the way, starting at a high enough point, it's going to make it all the way over to the coast. Okay? That's what this guy is here, the transition state for the uncatalyzed reaction. What the enzyme does is says, well, this is really a stupid way to do it. Okay? Why should we go to the tallest peak? All we have to do is find the pass. We find the pass. Well, as long as we get the thing to the pass, and there's nothing higher than that pass, we get it all the way over to the coast. So we don't have to push it up nearly so high to get it where it's going to roll back down over to the coast. And that's what's happening with an enzymatically catalyzed reaction. The enzyme is finding a transition state that is much more favorable and is lower in energy. As a consequence, that means, therefore, that a higher percentage of molecules will make it to the transition state and will, in fact, react. Okay, does that make sense? Okay. So that's what's happening. Now I want you to notice a couple things. Notice that in both the uncatalyzed and in the catalyzed reaction, we don't see any change in the overall delta G. There's the starting point, there's the ending point for both of them. So we're not changing the delta G. Enzymes do not, underline, do not change delta G. The overall change is exactly the same for those two reactions. However, because the enzyme can get a lot more molecules to this transition energy very quickly, the enzyme speeds the reaction. Now, enzymes do not change the equilibrium. That is, they don't change the ratio at the end, meaning that enzymes also facilitate the reverse reaction, and they facilitate the reverse reaction speeding up also. Why? Because again, if we start here and we go back up over here, it's easier to get to this point than it is to get to this point. It's much easier for the reverse reaction to come to equilibrium with the forward reaction. So enzymes work both ways. Enzymes speed reactions by speeding both the forward reaction and the reverse reaction. Okay. So that's how enzymes work. Now let's look at enzymatic reactions in a practical sense, such as we might look at in a laboratory. Okay? So notice that what I have here is a plot of reaction velocity on the y-axis, and I'll explain that to you in just a second, and substrate concentration on the x-axis. How would I generate information like this? Let's think about this first. So first of all, reaction velocity. When we think of reaction velocity, it's not that different from an automobile's velocity. An automobile's velocity we're calculating as miles per hour or kilometers per hour, right? Depending on where we're from or where we live. All right. By contrast, okay, an enzyme is catalyzing a reaction. So we're looking at the concentration of product divided by time. The concentration of product divided by time. That's what a reaction velocity is. Okay? Now, what this is saying is that if we increase the substrate concentration, we get increasing amounts of velocity, and that's not totally surprising. We put more things in for the enzyme to work on. The enzyme's going to work, the reaction is going to go faster. We see this increasing very steeply to start. It's essentially a linear relationship, meaning there's a linear relationship between the substrate concentration and the reaction velocity, at least in the beginning. It doesn't stay that way. It doesn't stay linear. And there's a very good reason why it doesn't stay linear. Okay? Imagine that you are the president of General Motors, and you have the idea that we're going to make twice as many cars next year as we made last year. Given how many they made last year, this probably wouldn't be too big of a thing. Okay? Ha-ha. That was not the joke for the day, by the way. Okay? So there will be a real joke later. Okay? All right? But you decide we're going to make twice as many cars. So you go out and you order enough parts to make twice as many cars. Okay? And you take them to your factories, and the factory workers start putting the cars together. And they might be able to make twice as many cars. They might be able to make them coming off of the assembly line twice as fast as they were before. Because last year they were kind of standing around a lot. They weren't doing a lot. And then the president says, oh, well, if we can do twice as much, let's do 4 times as much. Because now we're going to start shipping them abroad and doing all this. All right? 4 times as much is going to be harder for the factory. Why is it going to be harder for the factory? There's only so much throughput that they have, right? There's only so much that they can do. So a factory has a limited capacity in terms of how many cars it can put out per time. An enzyme has the same issue. An enzyme can only put out so much product per time. So if we keep adding more and more, eventually the enzyme says, whoa, slow down, man. I'm working as fast as I can. And that's what happens when we get way out here when we reach something called maximum velocity. That's the maximum capacity of that enzyme to catalyze a reaction. Just like General Motors has a maximum capacity, so too does the enzyme have a maximum capacity. Well, the president of General Motors sits around and goes, what was I thinking? Okay, we've only got so much capacity. What we should do is we should make more factories, right? So we go, in this day and age, probably to China, and we decide we're going to build some more factories over in China so we can now double our capacity. Because we couldn't do it. We reached capacity here. We can't do any more. So we're going to go and build some more factories. When we build more factories, do you suppose capacity will go up? Absolutely. There'd be no reason to build factories if that weren't the case. Okay? The same thing happens with enzyme. Let's say I do a separate set of reactions and I use twice as much enzyme. I've just doubled capacity, right? I'm going to make twice as much product per time, and I will reach twice the maximum velocity that I did with this set of reactions. That makes sense? Okay. So maximum velocity is something that is not a constant for an enzyme. It depends on the amount of enzyme that I use. If I double the amount of enzyme, I will double the maximum velocity because I now double the capacity of the enzyme to catalyze reactions. Okay? If you guys learn that, you'll learn something that the majors in biochemistry sometimes don't pick up. Okay? Well, it turns out maximum velocity is not a real valuable parameter in terms of describing an enzyme, because if it depends on the amount of enzyme, how can I compare one enzyme that catalyzes one reaction with another enzyme that catalyzes a different reaction? I can't compare the two, because it's going to vary. There's all kinds of variables in terms of how much enzyme I used, et cetera, et cetera. Well, to simplify things, there's another parameter that we use to describe what an enzyme's capacity is. Okay? It's called kcat. K with a subscript of CAT, which stands for catalysis. Okay? Kcat is determined by first determining the maximum velocity for a given concentration of enzyme. So a maximum velocity for a given concentration for this given concentration is right here. If I take the maximum velocity and I divide it by the enzyme concentration, now I've normalized it for all enzyme concentrations. So kcat is equal to Vmax, which is the maximum velocity, Vmax, V with a lowercase max, all right? Vmax divided by the concentration of enzyme gives me kcat. Kcat is also called the turnover number. And I'll show you some more on that in just a minute. Does everybody understand mathematically what kcat is and why kcat's important? No, okay. So kcat is important because it normalizes the amount of enzyme. Vmax varies with the amount of enzyme. Kcat is a constant for an enzyme. It's a constant for an enzyme. Vmax was not a constant. We didn't have that option, right? Because it varied as the enzyme concentration varied. Now I've got something that I could say, okay, here's the kcat for this enzyme. Let me give you an example. Remember the enzymes I talked about the other day, and I said that carbonic anhydrase had the ability to make 1 million molecules of product per molecule of enzyme per second? Everybody remember that? Okay? That's what kcat was. So kcat would be 1 million per second, meaning 1 million molecules of product per molecule of enzyme per second. If I compare the kcat of carbonic anhydrase to, let's say, a DNA polymerase, depending on its source, might do as many as 1,000 per second. But that's a long ways away from 1 million. I get an idea about the relative capacities of these enzymes. Yes, sir?
Are you keeping your changing substrate concentration, keeping your enzyme concentration the same in that graph?
So his question is, am I keeping substrate concentration and enzyme concentration? I'm changing substrate concentration, but am I keeping enzyme concentration? In a given graph, yes, I am. Because if I varied enzyme concentration, then this wouldn't have any meaning. So that's a good question. Let me just tell you how you would set up an experiment like this, because I think you should know this. All right? I want to determine what Vmax is for an enzyme. How would I determine that? Well, here's what I would do. I would go get 20 tubes. And into the tubes, I would put some buffer so my enzyme stays folded and doesn't get denatured. I would put varying amounts of substrate. So one might have 0.1, another 1, another 10, another 30, another 40, etc. So I've got 20 tubes with 20 different concentrations of substrate. That's the only variable in this experiment. Then to each tube, I add exactly the same amount of enzyme. And I let each reaction go for the same exact amount of time. And then I measure the product. I measure the amount of product that is produced at the end of that time. Concentration of product divided by time gives me velocity. And now I plot them. So at the lowest substrate concentrations, I see very little velocity. Increasing substrate concentrations, I would have 20 points. And I would draw this line through the points. And I would eventually get up over here and I would discover, whoa, it is flattening out. Okay? The flattening out, it flattens out at maximum velocity. Gesundheit. What I've just described to you is that the enzyme is becoming saturated with substrate. Just like General Motors was becoming saturated with parts and no ability to do throughput, the enzyme was becoming saturated with substrate. Okay? Now, not all enzymes work at the same rate because enzymes have different abilities to bind substrate, different abilities to change themselves and catalyze the reaction. We'll talk about some of that. So they don't all work at the same rate. Keep that in mind. Okay, other questions about this? Does that make sense? I'm sorry?
What units for kcat?
Okay, what are the units for kcat? So kcat is equal to number divided by time. So 1,000 per second is actually the unit. So the units are per time. And what that means is 1,000 molecules of product per molecule of enzyme. So the molecules cancel out per second. That's why it comes out as per second. Okay? Okay, so you've learned a very important principle in kcat. Kcat's a very, very valuable number to us to know. And we can't get kcat unless we determine maximum velocity. We have to know maximum velocity at a given concentration because, remember, maximum velocity divided by the enzyme concentration tells us the kcat. Okay. Let's see. Wow, there's an enzyme. Okay. And Enzymes have hydrogen bonds, not a surprise. Okay, and let's talk about mechanisms of catalysis. All right, so one of the ways that you were taught how enzymes work in basic biology classes probably is wrong. It's probably wrong, okay? And it's an important model. It's useful in one sense. It tells us a lot about enzyme shape and substrate shape, okay? This model is called the Fisher, lock, and key. The Fisher, lock, and key model of catalysis looks like this. In basic biology, you're told, okay, enzymes fit their substrates like a key fits into a lock. So that key is the substrate, the lock is the enzyme, and so that substrate comes along, the enzyme binds it, and you put the wrong key in there, the enzyme, the lock won't touch it, etc., etc. Right? You guys have all heard this before, right? The Fisher, lock, and key is very good at explaining why enzymes only bind specific substrates. It's very bad about telling us anything whatsoever about how an enzyme works. So it's good at telling us about how it binds a substrate, but it's bad about telling us how it works. In other words, what we're seeing here is a substrate binding to an enzyme. This part is really good. But then we get to that thing on the board that says, then a miracle happens, and we get product, right? Well, we want to have a little bit more than just a miracle happening. And that's what the other model explains very nicely. Okay? The other model is a more modern model, and it's called the Koshland-induced fit. Okay, you can see it right here, Koshland-induced fit model. And the figure here is not ideal, so I have to do a little explaining to you. If you look at this figure carefully, you'll see on the left that the enzyme and the substrate don't have exactly the same shapes. The enzyme has the sort of outlines of the substrate, but it doesn't match the substrate exactly. We can imagine that this binding of this enzyme might occur by a process that might involve, let's say, 3 steps. The first step, this guy right here, this middle prong, matches this prong fairly well. We can imagine that when it binds to that prong, that changes some chemistry, it changes some hydrogen bonds in the enzyme so that the enzyme shape now adjusts. And guess how it adjusts? It adjusts to fit the substrate properly. So the A site forms upon that adjustment, the C site forms upon that adjustment, and now we're at the ES complex just as we were before. But there's a difference now compared to the Koshland model. We had to change the enzyme in order to get to this point. We have transiently changed the enzyme. Well, enzymes are kind of like you are on maybe Monday morning when you're laying in bed and you really don't want to be moved. You don't want to be changed, right? I know I felt that way this morning. You're going to resist that change. You've got some tension because somebody is saying, get out of bed, right? You have some tension, and that tension now is present in this substrate complex. Get out of here. The enzyme is ready to get this damn substrate out of its site, but because of that tension, it changes the substrate. So now we see a shape changing that's happening as a result of the tension that the enzyme has felt from this change during the catalytic mechanism. So, what the Koshland-induced fit model tells us is that not only does an enzyme change a substrate in making product, it tells us that the substrate transiently changes the enzyme as well. Notice I said transiently, because when the enzyme kicks this modified substrate out and makes product, the enzyme goes back to sleeping on Monday morning, just as it was. The enzyme gets back to its original state. That's why it behaves like a catalyst. A transient change, okay, a transient change that creates a tension. That tension is necessary for making the product, and the enzyme goes back to being the way that it was before. Make sense? Questions about that? Yes? Does enzyme do what?
Does it change shape?
The enzyme has changed shape here compared to where it was here. Yes.
But it doesn't change after that?
So once it's released this, it goes back to its relaxed state, right back here. Yeah. Yes, sir.
So when you say it increases the tension of the enzyme, are you saying it increases the potential energy of the enzyme?
It's changing, exactly, it's changing some serious parameters inside the enzyme that now the enzyme wants to get back to where it was. And so
If the potential energy increases, why did it accept the substrate in the first place?
the binding of the substrate had bonds that now affected bonds that were in here. So there were interactions that were happening here. Maybe there's a hydrogen bond here that now puts a negative charge, a partial negative charge where there wasn't one before, and the enzyme changed shape to adjust to that. Okay? Yes?
Is the hydrogen bond the strongest type of bond that's going to bind the substrate to the enzyme?
Is the hydrogen bond the strongest type bond that's going to bond the substrate to the enzyme? For most reactions, I would say yes. We'll talk later about suicide substrates that actually make covalent bonds with enzymes, and they, in fact, kill the enzyme. So there are transient covalent bonds that are made, and we'll talk about those as well. But from the purpose of binding, hydrogen bonds really will be up there. Yes? Yes, ma'am. That's okay.
So if it's not the exact shape of the substrate, what if there's a similar substrate that it normally would?
Oh, okay. So if it's not the exact shape of the substrate, does that mean there's flexibility in substrates that it can bind? Depending on the enzyme, yes. Some enzymes can bind a wide variety of substrates, others can't. So we'll talk about proteases later that can accept a variety of different substrates in at their active site. Others won't do so well. It varies with the enzyme. Yep. Yes, sir.
And that would make it have a different K-cat for different substrates.
It will. Oh, very good question. It will have different K-cats for different substrates. You bet. Okay, how about a joke? Okay, all right. So, this is one of my favorite cute jokes, okay? So, this is about Artie the Hitman. Have you heard about Artie the Hitman? If you have, too many people take my class or heard about it otherwise, so don't give it away. All right. So, Artie the Hitman. So there's this little guy, and he decides that he wants to be a hitman, right? So he goes out, and he decides, well, if you're going to get ahead in this world, you have to advertise. So he starts posting, little note cards. I will kill somebody for $1. Okay, he puts them all around his neighborhood, And so this guy sees it and goes, oh, wow, he said, I'd like to have my wife killed. And so he grabs his card, he takes it home, and he calls up Artie and says, you're killing somebody for $1? And he said, yeah, I'm just getting started. So, if get a good customer base here, then I'll be making, I'll charge more later. But just since I'm getting started, it'll only be $1 for you. And, well, this is great. He's gonna make some money. And so the guy says, well, I'll tell you what. He says, my wife. So he says, the two guys meet, and he says, shows him a picture of his wife and everything. And he says, she's going to be down at the grocery store later. He said, I want you to kill her there. And he goes, oh, okay. And he said, how should I kill her? Oh, I get to decide that too? Well, I aim to please. I'm working to please my customers. So why don't you strangle her? Okay. So sure enough, the guy already goes out to the grocery store, and he walks in there and looks, and there she is in the produce section, and she's all by herself. It's perfect. This is the way he wants to get his career started. So he goes there, he grabs her, and he strangles her right there in the produce section. And he's feeling really smug, and he turns around and, somebody saw him, right? Well, of course, if he has a witness, then, of course, his career as a hitman is over. So he goes, he chases down the witness, he grabs them, and he strangles this witness right there, okay, in the meat section. Well, not his lucky day. Somebody in the meat section sees what he's done, and he goes, and he grabs this person, and he strangles them over in the deli. Well, by now, he's ready to get out of here. He goes racing out of the store, and the police see him racing out of the store. The reports are that there's been 3 people murdered there. They go, they grab him, they arrest him, and in the newspaper the next day, the headlines read, Artie chokes 3 for $1 at the grocery store. That's the best reaction I've ever had for that joke. You see, Artie was, okay. All right. Artichokes, 3 for $1. Now, don't go tell everybody so next year they know what this joke is, okay? I have a limited number of jokes. And okay, artichokes, 3 for $1 at the grocery store. All right. Well, we've talked about, was that good enough, by the way, Julie? That was okay? Okay. We've talked about kcat. We've talked about Vmax. There are some other parameters about an enzymatic reaction and about an enzyme that we need to know. All right? So let us talk about those. And the first of these relates to initial velocity. This is now graphically showing you what I described to you earlier. It says that if we look at this reaction very quickly, not in terms of substrate concentration, but in terms of time, we discover that this relationship is linear, okay, to start with. It's linear to start with. With increasing concentrations, S4 is greater than S1, we see that we're still linear, but it's tailing off. Okay? This is fairly linear out here, fairly linear here. All right? The increasing concentrations cause it to start tailing off faster. Why is this the case? The reason that this is the case, okay, has to do with the fact that the enzyme catalyzes the reverse reaction as well as the forward reaction. The longer we let this reaction go, the more likely the enzyme will start converting product back to substrate. In other words, it's trying to establish equilibrium. So the bottom line of what this message is that when we do measurements of velocity, we always do it in a very short time frame. You'll see them written in your book as V0, meaning very short time frame. If we go too long in our measurement of the velocity, we're not going to accurately measure what the actual velocity is, because we're going to start measuring the backwards reaction, which is going to subtract from our calculation. So we have to measure things very quickly, very early, in order to accurately determine the velocity. And that's really what we're interested in. All right. Now, this figure shows yet another parameter about an enzyme that we need to be aware of. There's Vmax. So this means that we did all these reactions. There's those data points. We did all these reactions with the same concentration of enzyme. So we could determine what the Vmax was. So we could determine what the kcat was. But kcat just simply tells us how fast the enzyme works. It doesn't tell us anything about how well the enzyme binds to its substrate. That's useful information. You saw from how that shape of the enzyme was and shape of the substrate was that we might expect there would be some varieties of ways in which those things could bind. And there are. Different enzymes have different affinities for their substrate. Affinity meaning desire to hold on to. Okay? So we have to have some way of measuring that affinity. That affinity is measured by a parameter known as Km. Okay? Km is measured by doing just what you see right here. You do a plot of velocity versus substrate concentration. There's the V0. There's that initial velocity versus substrate concentration. We establish what the Vmax is, and then we say what was the substrate concentration that gave Vmax over 2. That turns out to be Km. So I'm going to give you the definition, then I'm going to tell you about why we do this. So Km can be defined in a couple of ways. It is a measure of the affinity of the enzyme for its substrate. We'll talk about how it varies in a minute. Okay? Km is measured as the substrate concentration that gives Vmax over 2. Notice I said that very carefully. It is the substrate concentration that gives Vmax over 2. It is not Vmax over 2. Vmax over 2 is a velocity. Km is a substrate concentration. Km is the substrate concentration that gives Vmax over 2. Now, why do we pick Vmax over 2? We're interested in how well the enzyme binds to its substrate. Why didn't we pick Vmax? Well, as you can see from this plot, the amount of substrate it takes to get to Vmax is essentially infinite. It's essentially infinite. Right? So that number is going to be basically infinite for any enzyme. It doesn't tell me anything. But what it takes to get to Vmax over 2 is distinctive for the enzyme. Let's think I've got two enzymes. One that has a high affinity for its substrate, one that has a low affinity for its substrate. Okay? The one that has high affinity for its substrate is going to have a Km of a certain value. The one that has a low affinity for its substrate is going to have a Km of a different value. Something that has high affinity, do you suppose it's going to have a high Km or a low Km? It's going to have a low Km. It means it takes less substrate to get to Vmax over 2. So low Km means high affinity. High Km means low affinity. Okay? Now, there are enzymes that catalyze identical reactions. And those different enzymes can have different Kms. We can also see how the Km for an enzyme catalyzing a reaction will vary depending upon the substrate, if it can handle more than one substrate. But Km always gives us a measure of the affinity of an enzyme for its substrate. And here's the kicker. It's a constant for a given enzyme. It doesn't vary with the enzyme concentration. It's a constant. So the two constants that I've given you then are kcat, which is molecules of product per molecule of enzyme per second, and Km, which is the measure of the affinity of the enzyme for its substrate.
Low Km means high affinity because it takes less substrate to...
Low Km means high affinity because it takes less substrate to get to half of Vmax. So something that has a high Km means it has low affinity, meaning the substrate has to literally start pounding on the enzyme's head before the enzyme wakes up to the point of doing Vmax over 2. Yes, ma'am?
So enzymes that have multiple substrate is still the same Km for the enzyme? Or
So her question is, if you have an enzyme that has multiple substrates, does it have the same Km for all the substrates? The answer is no. So its Km will vary for the substrate for the reaction. But again, if it's a different substrate, it's a different reaction being catalyzed as well. Yes, Stephanie.
How do we determine Vmax? Is that number given?
So there's a couple ways we're going to determine Vmax. One is by doing a plot of this over a wide variety of reactions, and we can determine essentially where that thing is flattening out.
Even though it takes an infinite number of substrate concentrations?
Even though it does, we can get pretty darn close to it up here. Okay? What I will give you later is another way of determining it using a different graphical plot where you can actually eyeball it much easier than you can here. But this is one way of doing it. So a V versus S plot, you can get a pretty good idea pretty quickly. Yes, Brooke?
How is the Km related to the reverse reaction?
How does the Km relate to the reverse reaction? I'm not sure I understand the question. But the Km is specific for a substrate. So a substrate, in the reverse reaction, the product is the substrate, right? So you would have a Km specific for that product binding to the enzyme at that point.
So it's a completely unique range.
They could be. They could be, yeah. Question?
So how do you not determine enzyme concentration?
Yeah, it's a good question. And mathematically, I would have to show you the answer to that problem. But suffice it to say, and I'm not going to go through the math of it here, but suffice it to say that it is a constant for a given enzyme. Julie?
So for these reactions, we're assuming that they wouldn't go to completion without the enzyme. So we don't have to worry about rates of reactions without enzymes.
So her question is, may we assume that the reaction would not go to completion without the enzyme? Okay? The reaction will go to equilibrium either with or without the enzyme. All that an enzyme does is it speeds the rate with which it gets to equilibrium. But in both cases, it goes to equilibrium. It doesn't go to what we think of as conclusion. That's something that we've got to wipe out of our heads from freshman chemistry. So no reaction goes to conclusion. It always goes to equilibrium.
Yeah, but I mean, we're assuming that it will go whether the enzyme's in there or not. The enzyme just...
It will eventually,
Okay.
yeah. So I gave an example the other day of a reaction that would take 17 million years
Yeah.
to get half done.
Yeah,
Right.
but in some of these, we're assuming that that rate isn't effective of Km or of any of our constants or Vmax
Yeah,
or
so there's not a relationship between Kcat and Km, if that's,
No,
if
yeah,
that's the
no.
question. There's not a relationship between them,
But
right?
the rate of a reaction without the enzyme isn't a factor at all. Like, what if we have
No, the rate of the reaction without the enzyme is not a factor. That's correct. Yeah, yeah. Okay. Okay. So, Km and Kcat, we're making very good progress. So you guys are getting this well. Very, very pleased with that. Okay. All right. Now, this, getting back to Stephanie's question, was, well, how do I determine Vmax? That's kind of hard to figure out. Where do I draw the line? Is it here? Is it here? Where do I draw the line? Okay? It's kind of like going out drinking on Thursday night. You don't know where to draw the line there either. Another joke. Another joke. Okay? All right? Well, we're going to draw the line, all right, in another way. When I did that experiment that I described to you, I had 20 tubes, and I had 20 different substrate concentrations, and I determined 20 different velocities. I generated basically 40 different numbers, 20 velocities and 20 concentrations, right? If I took each one, the velocity that corresponded to each concentration, and I inverted it, took the reciprocal, I would have, instead of V, velocity, I would have 1 over V. And instead of substrate concentration, I would have 1 over substrate concentration. If I took those values and I plotted them, something cool happens. Okay, it's not a miracle, but the something cool that happens is that hyperbolic plot that we saw before becomes linear. The linear is shown by these dots going along right here. So I've plotted 1 over V versus 1 over S. My hyperbolic data becomes linear, and now, look at this. These guys line up, and I can draw a straight line through them, and I can draw it all the way down to the x-axis over here. The places where this line crosses the y-axis and the places where it crosses the x-axis are very useful entities for me. The place where it crosses the y-axis has the value of 1 over Vmax. I didn't have to eyeball it. I didn't have to guess it. I simply had to be able to draw the straight line and say, there is 1 over Vmax. If I take 1 over Vmax, I get Vmax. Very easy to do. Conversely, in addition, as the line gets extended down into the negative region, notice we're down here in negative substrate concentration. That's not even possible. So that's why all my points are over here in the positive region. But if I take that intercept where it crosses the x-axis, that has the value of minus 1 over Km. So if I take that number and I take minus 1 over that number, I end up with Km. So this type of a plot is called a Lineweaver-Burk plot. Lineweaver-Burk. Lineweaver-Burk. Lineweaver-Burk plots are also known as double reciprocal plots because they plot 1 over V versus 1 over S. Now, Lineweaver-Burk plots are very useful for us, and we'll see when I talk next time about enzyme inhibition how very useful overall they are for us. That's a good place to stop. Let's stop there, and I'll see you on Wednesday. What's up, Katie?
Okay, well, I just have a question from last time with the 2,3 BPG.
Yep.
So if someone was like in an area like where there's like low oxygen concentration, like in like high altitude or something, like would the body like produce more like?
Actually, that's an interesting question. The answer is yes, it would. Okay. And there's several reasons why that happens, but the body will do that, and it's partly for the same reason the smoker produces more 2,3-BPG. Make sense?
Yeah.
But I'd have to show you another step before you'd understand that. But you're exactly right. It would.
Okay.
Okay. Hi.
really quick.
Yeah.
So just examine, like, when you talk about the molarity in this problem here, you have the molarity of buffer.
Yep.
Are you talking about the molarity of the acetate, protonated and not protonated, altogether?
Buffer is always equal to weak acid plus salt.
So you have to do
Okay. So it's all of the A minuses, no matter what's hanging on to them.
A minuses plus HAs. Right. Yeah. Okay. Let's fall me back here, Kelsey. That's okay. You guys have questions also?
I have a joke to tell you. It's an enzyme joke.
Oh wow. Okay. Well, bring it up to me. I definitely need more jokes.
Right now?
Yeah.
Good luck on your mids.
What's that?
Perfect enzymes,
Yes.
are they linear for their graphing graph?
No. I'll talk about perfect enzymes. I'm sorry. I'll talk about perfect enzymes next time. I ran out of time today, but yeah. Enzyme joke.
It's risque.
Oh, all right. Look out. I'm warned.
All right. What's the difference between an enzyme and a hormone?
You can make an enzyme.
You can't hear the enzyme.
You can't. Okay, that's fine.
I heard that when I didn't get it, and I started like actually listing off.
You can't make an enzyme. Is the way you tell the joke. Yeah.
Oh, yeah. I like it. Okay. Anyway, I just thought I'd
I won't
share.
tell that one to